Oh, yeah. Cool. All right. So welcome to the Altium workshop. Yep, I hope you had a chance to have a read of the pre-reading that I put together last year. That'll cover all of the terminology used in PCBs and some of the weird things, as well as the actual board that we're going to design today. Please jump in at any time if you've got questions, because particularly if you're running behind, because I can't really tell where you guys are at. So raise your hand. Oh, maybe don't raise your hand because I'm not sure I can see that, but type in the chat or just speak out. Yeah, all right. First off, does everyone have Altium open? You should have something kind of like this. You might have like the home page, but
yeah.
Yep, cool. So what you're going to want to do first is go File, New Project. And I think, Matt, I might just have people save them locally so that we don't fill the 365 with them. But I'll show you how to use 365 as well. So click on the left-hand side. You should have this APAC Monash Rover thing. That's our 365 workspace, which is basically like a Google Drive or like GrabCAD for Altium. Now, most of your projects that you make for the team, you'll save here. But because we're going to make like 10 different versions of the same board today, we're just going to save it locally onto your computer so that we don't make a mess. So just click local projects on the left there and then type in the project name, any name. So I'm just going to call it PCB Workshop Will. And the default save point there is probably fine. You can change it if you want. But this is where all of the other boards get saved when you pull stuff down from the 365. Once I put my name in, I'm just going to click create, and that will create this thing called PCB Workshop Will.project PCB, and you can ignore this one up here because that's the one I made as a reference for when I forget what to do. Cool. All right, so you should have that project. Again, let me know if you're slipping behind or you got any questions. We're going to now add a schematic to this project. So we're going to right click on it and go add new to project schematic. The other way you can do it is also select it in the projects panel here and go file new schematic. And then it will add that to here and it's called sheet 1. Alrighty, so first thing we're going to do is hit Control S and save it. And we're going to call this, we'll call this microcontroller. So we'll start with the microcontroller sheet. And I realize I'm going to need Slack actually, because I need all the part numbers. Cool, so you should have microcontroller sheet. And what we're going to do is we're going to insert our microcontroller. So if you went to the components workshop yesterday, you'll probably be reasonably familiar with the components and the manufacturer part search panels. Now, if you click down the bottom right here, this is the panels button. Now, this is all of the sort of menus that you'll need while you're making the board. The most common one you'll need is components and manufacturer part search. You might also use Explorer occasionally. Most of these other ones will automatically pop up if you need them. So we're going to click components and should look something like this. Now, does everyone have like this all bracket 77 at the top, or are you not connected to the components workspace?
Yeah, it shows up.
It's all good. Cool. So if we're going to do is we're going to go to, so this is the microcontroller we're going to use. I linked all of these in the useful info thread in the Slack. I just sent the part number there in the chat. And all you got to do is copy that into the component search. And you can see now we've got this part here. And so if you went to the workshop yesterday, you would have, if you're making this board, you would have spent the time to either download and import the footprint and schematic for this schematic symbol, or you would have made it yourself. So we're just going to right click and go place, or you can just click and drag onto the schematic as well. All right, so you should have the schematic symbol for your PIC. So we use PIC microcontrollers. Now the symbol here looks super like horrible because it's got all these different names for each pin. Don't stress about that. If you remember in the pre-reading, we had a look at the symbol here, and these colored pins are the only ones we actually use. We ignore all the other names. Basically, the pick, sort of like an Arduino, you can reprogram them to do different things. So like you can reprogram each pin. So like this pin here could be a PWM pin, or it could just be a general register output pin. All right. So the next thing we're going to do is grab our programming connector, which is this one here. So again, put that in your search and drag that on over here. So this is the programming connector. This is we just chose this connector because it's small, and we plug this in with the pick kit, which is what we program the picks with. Next up, we're going to grab the crystal. So crystal oscillator is what drives the clock of the processor. Yep, raised hand.
Yeah, sorry, just where are you getting all these part numbers from? I can't find it on the slide.
In the in the useful info thread in the Altium channel.
Thanks.
Cool. But I'm also just putting them in the chat, so you can copy them from there if you prefer. Now, obviously, what I'm not teaching you in this workshop is how to pick all of these components. For this schematic sheet, most of it's just going to be copying and pasting, because generally all the supporting electronics around the microcontroller are the same. Like you need the crystal oscillator, you need the programming connector. There's a few resistors and stuff you need as well. So that's not going to change. So you can usually just copy that. But if you were, say, for example, designing a new motor driver like we're doing at the moment, you actually need to find all the components you're going to use and check out the data sheets and make sure they're all compatible with what you want to do. So unfortunately, I can't teach you that, but it will come with practice. Now I'm just going to open up this. So this is what we're heading towards, and I'm just checking it because there's a lot that needs to be on here. Just a few things about moving components. So if you click and hold and then drag on a component, it'll move around. If you press spacebar, it will rotate around your mouse. And if you press X, it will flip horizontally. So if you want to like flip it vertically, you can rotate, press X, rotate again. Yeah.
You should also be able to flip horizontally by pressing Y.
Oh, there you go. Cool. Learning new things every day. So what we're going to do is, for this crystal, we're going to place the capacitors next to it that it needs, and the grounds as well. So if we look, this is the schematic that we're going off. So this uses two 10 picofarad capacitors, and then connects them to ground on either side. So we're going to type in 10 PF into our search, and we've already got a 10 picofarad capacitor here. Now you'd want to check, this is the exact one we want to use, but you'd want to check that it's the right, that it is actually 10 picofarad and that it's the right voltage, and the right footprint you want. So this is an 0603 footprint, which is, so if you did the pre-reading, it's 60 imperial mils by 30 imperial mils. And that's exactly what we want. Cool, so you can just drag one of those in. I won't drag the other one yet because I want to change some things first. Cool, so if you click on this, you can either double click the component and it will open up the properties panel on the right, or if your properties panel is closed, you can click on it and you can go to panels and then properties, and it will open up here. Now what I want to do, like this capacitor here, the thing with schematics is you need to sort of communicate to someone else that's looking at your schematic what is going on. And this part number being here is not very helpful for that. So what I'm going to do is I'm going to go to the properties and I'm going to hide the comment that has the part number in it. And all you do is you just click on that I there and it gets rid of it. It's still part of the component, but it's not visible. Some info that is useful is the capacitance. So I'm going to unhide the capacitance parameter. So it might be hidden away under here. And then I'm just going to move that down to next to the designator there. So now we're sort of communicating to the other engineer that's looking at this, what's going on. So let me just, so now how do we connect these together? So what you could do is just like put it right on it, and then it'll be connected by a wire. The way you do it generally is if you can click on, geez, I don't actually know where the wire tool is. Oh, here it is. Yeah, you can click on the wire tool, which is in this toolbar up here, the two blue lines, and you can click once to start and then again to finish. If you need to go around a corner, you can click once, and you can see it has this like right angle stuff, and you can press space to like switch which way it bends, and you can kind of route it all around however you want, and then you just press escape to finish. So you can click the wire tool here, or you can just press Control W, and that does the same thing. Control W is your friend. You will become very familiar with that as you go. Cool. So place one. I'm just going to copy this capacitor and place another one over this side as well, and then connect this one up too. And then we're going to connect both of these to ground, and also connect the ground pins of the crystal to ground. Anyone stuck anywhere about the crystal? All good. Cool. All right, so that's the crystal in. Now let's have a look here. What's next? So let's do the programming connector next. So you can see here we need a 10K resistor and a 470 ohm resistor. So we'll go here and we'll type in 10K into our component search, and we'll pull this out. So again, someone's already made this 10K. Turns out it was actually Christos, I think. And again, I don't really care about this part number, but I do want the resistance. So I'm gonna unhide the resistance and hide the part number. So to do that, you double click on this to bring up properties, and you click the little I next to comment, and then click the I next to resistance to show it. It might be hidden under show more. You can like hit star here, and then they'll appear at the top if it's something you want to see more often. Cool. So we need to hook up the resistor between VCC and M clear pins. So I'll move that down here. And again, we just Control W to route this here, and again to route that one. And then we also need this 470 ohm resistor. So back to components, type in 470. And so that one's a capacitor. That's the resistor we want. So you can check if you click properties here. Wait, no, that's not it. You can see show more. You can see the resistance here. So I'm going to star that so I see it more, and probably hide some of these. And now you can see the resistance is more visible. Cool. So I'll drag that in, and once again we've got the comment that we don't want, and I'll show the resistance. There we go.
Sorry, what resistance? 470?
470, yeah. So you can sort of drag around these designators as well. If you press Control, it will like not snap to the grid, but you typically want it to snap to the grid. There's also like, if it's justified, so at the moment it's justified to like the bottom left of the grid. You can make it so it justifies to the top left or the right or whatever, if you want it to. That's where the option is. Okay, so that's those resistors. Anyone stuck?
I just have, so my wire is kind of just like going through the resistor and then down, instead of it's going across and then down instead of down and then across.
Oh, so it's like that.
Yeah.
Yep. So instead of routing directly to here like that, click here and then go down, click again, and then go across.
I see. Thanks.
Yeah. It's worth noting, whenever you see this little dot, that means they're connected. So if I actually route this up like that, oh, that's probably a bad example. If I bring my resistor down one spot, this is a bit hairy. Hang on. So I do this, and then if it route it like that, this trace is actually connected to both sides of this resistor now. And whatever is like displayed in your schematic is how it's actually going to be connected on the circuit board when you put it together. So got to be a little bit careful about these little dots, make sure they're doing exactly what you want. All right, bit about selecting stuff. So if you want to select a group of components, you can just like click and drag over the whole lot. If any of you went to the SolidWorks workshop, you'll know that if you drag from the left to the right, it selects everything that is fully enclosed by the box. But if you drag from the right to the left, anything that's touching the box, so like this connector here, will be selected. So depending on what you're doing, it can be helpful to just know that little trick. So I'm just going to drag this down to about here, and I'm going to connect the M clear pin to the IC. Next up, I'm probably not going to do the routing exactly how I've done it here, but you can see that there's these little, there's the 3v3 designators and the grounds, and then there's also these labels here, these net labels. So let's do those now. So this VCC pin needs to be connected to 3.3 volts. So you get this from the same place that you get the ground power port. If you right click on this, you'll get a bunch more options. So I'm going to grab this +5 power port. Now it's not what we want, but you can double click on this and then rename it to 3v3. So the 3v3 is just a shorthand for 3.3 volts. That's very standard. And the thing with these power ports is, although they're not connected, if I put another one over here, although they're not connected physically in the sheet, these are connected in the back end. So it just sort of neatens your schematics a bit. You can just place the power ports wherever you need them, and they'll all be connected exactly how you want when you actually move to the routing stage. So we've got that one there, and then we're also going to need a ground one, and then we've got PGD, PGC, same as the connector here. So I'll right click again and get a power port, and I'm just going to move this to there. And use Control W to route. And then here, I'm just going to run 2 wires out from these 2 pins. And if I right click on the wire tool, there's this net label tool. So I'll click once there, I'll click once there. And then I just double click here and I can rename it to PGD and PGC. All right, that was pretty quick. Did anyone fall behind?
Where is the label tool?
Yep, so it's under the wire tool. So if you right click the wire tool, you go net label.
Thanks.
Just a random note, NC stands for no connect. So don't connect anything. In this case, you won't actually break anything, but sometimes ICs won't function properly if you connect things to them. All right, so similar to these power ports, these net labels will connect things together on the schematic. Now there's a bit of stuff about scoping that I'll get into in a minute, but if we put another wire somewhere on the schematic with this PGC label, they will be connected together, even though they're not physically drawn to connected on the schematic. So let's take a look at the microcontrollers at what we're heading towards. So this PGC pin connects to pin 15, which is this PGEC2 pin. So what we're going to do, we're going to draw 2 lines from pin 14 and 15 out, and we're going to add 2 net labels here. And this one's PGD, and this one's PGC. Now you got to be really careful, both with your net labels and your power ports, that you're typing them exactly the same and that they're case sensitive. One thing I see all the time is people will have one port that's labeled 3v3, and then I'll do another one that's called 3.3 volts. These are not connected. These won't connect together. So be vigilant with that when you're designing it. But now we've got PGD connected from the connector to the pins on the PIC. Everyone follow that? So what we're going to do is do the same thing, but for the oscillator. And so you guys can do this. So we're going to connect it here to OSC1 and OSC2. It doesn't matter which side of the oscillator you do. So I might do it like this. All right, so you can see I've just routed OSC 1 and 2 to the PIC with the net labels. Anyone missing that? Cool. All right. So now there's just a bit of random capacitors we've got to do. So you can see there's two 100 nanofarad capacitors and this 10 microfarad capacitor here. So if we go to components and we do 0.1 UF, or I wonder if you do 100 nanofarad, yeah, if you do 100 nanofarad, it'll come up as well. And we've got this 0603.1 microfarad capacitor. So we're just going to grab that. Again, we're going to hide that and give us the capacitance because that's what we care about. And I'll just duplicate this because we need two of them. So one of them runs from AVDD to the capacitor to AVSS, and the other one runs from VDD to the capacitor to the SS. And there's two here, so just connect those together. Reminder, if your wire is like elbowing the wrong way, you can press spacebar to toggle it. And then we need 3.3 volts on VDD and grounds on the other side. So I'll grab my 3.3 volt power connector and a ground. And there you go. Lastly, we need this 10 microfarad capacitor. So if you type 10 UF, you'll get it. This is a tantalum capacitor, which is a different material that some capacitors come in. It's special because it has what's called a low equivalent series resistance. So basically all capacitors have a small like series resistance value. And in this case, you need a low ESR for this pin here. So as we go, we might, because this workshop's quite new, there's not many components in it, there's only 70. But as we go, we might develop more 10 microfarad capacitors in here. So you'll need to sort of check exactly what they are and if they suit what you need. But here it's up to 16 volts and this pin only goes up to 3.3. So we know we're safe there. Okay, and then lastly, we just need to do the ports. So we're going to do today, in today's workshop, we're going to do what's called a hierarchical schematic design, which is it's very common in the team. It's what we prefer because it's very easy to understand. Whereas you can do what's called a flat design, which is quite easy to sort of do, but if you're trying to understand how the information flows through all the components, it gets quite messy very quickly. All right, so we're going to grab this little D1 yellow shape here. This is a port. So if you just click that, and when you place a port, when you click the first time, it will place the left edge, and then the right edge you can make as long or as short as you want. Typically, it only needs to be about that long. And we're going to connect up. So you can see here, we need to connect this GPIO pin, the SCL SDA lines for the I2C, and then the CAN, RX, and TX lines. Now, on a PIC, CAN lines can go to any pins. So we'll grab this. So this one here, this was N wake. So lowercase n, capital wake, and that goes to the CCS sensor that we'll be putting on in a minute. I'm just going to copy this a bunch of times. You can see there's like these big microcontroller things on here. I think you can turn that off. Oh yeah, this cross-reference thing here, if you don't want this, basically this tells you which schematic sheets the ports appear on. So I'm just going to hide that by selecting them all, and under properties, there's this cross-reference microcontroller thing. You just hide it there. So the first one's NWake. The second one is SCL. Third one's SDA. Fourth one is CAN _RX, I think. Doesn't really matter. Yep. And the last one is CAN _TX. Now you can see that all of these are currently IO type unspecified. So it's not absolutely critical, but it's worth doing. You can define whether the pins or the ports on your schematic sheets are inputs or outputs. So this N-wake signal comes from the PIC to the microcontroller. So we're going to define this as an output. So it's an output from the sheet. the SCL and SDA pins, I2C is a bidirectional communication protocol. So we're going to change these to bidirectional. And then CAN TX is an output because it goes from the microcontroller to the bus, and CAN RX is an input. Lastly, we're just going to connect all these up with wires to the thing. All right, now, okay, did anyone miss any of that? Does that all make sense?
Yes, I missed the SCL, SDA, and Wake.
On which direction they are?
Yeah.
Yep, so Wake is an output and an SCL, SDA are bidirectional.
Yeah.
Ultimately, it doesn't change, like it's not like the traces on your board are going to be like only let information flow in one direction. The traces are physical copper, that's all they do. But when you put your schematic together, it will raise an error if there's something that's going in the wrong direction. And that's very helpful for catching mistakes. All right, and I think that's it for the microcontroller. So this is essentially the process you go through. To reduce errors, you can copy and paste this from other schematics, but you just got to make sure that you are copying the right thing. Yeah, Josh, you got a question?
Yeah, so I set the CAN RX as an input, but the arrow is still like, it's still pointing in the wrong direction. And I'm not sure why.
So when there's no wire to connect it to it, it doesn't actually know which way to face yet. So as soon as you connect the wire, it should go left.
I see, thanks.
Yep, cool. Same thing for CAN TX. If I connect the wire to the other side, it'll flip around. Yeah, cool. All right, so just hit save on that, and then we are basically done with the microcontroller sheet. Yep.
What about the turning the C question mark into C1 and C2?
Yep. That's a good question. So we'll actually do that at the end.
Cool.
But yeah, so all of these designators right now are just J unknown or C question mark. You can do it all. If you want to, you can manually make them like R1, R2, R3, but what we're going to do is automatically do that at the end, just to make our lives easy. I guess I should have explained as well, just like general movement. So mouse wheel is scroll up and down, control wheel is zoom in and out, shift wheel is left and right. You can also right click to pan if you prefer, and you can middle click to zoom, but I like control and shift. Also, if you're using the space mouses in the workshop, they work with this. So yeah, cool. All right, so now we're done with this sheet, so we'll add another sheet, and we're going to immediately save this. So remember, file, new schematic, or you can right click the project, go add new to project schematic. So we'll immediately save this, and instead of calling it sheet 1, we'll call it top sheet. So the top sheet is sort of the like top level function in your programming, or like a top level block diagram. It's really a block diagram, but some people find it easier to understand it like a function. So we've got all these subsheets, and they're sort of like functions. So you can call them repeatedly in your schematic if you need to replace them multiple times. So what we're going to do is we're going to click, so this green symbol, this sheet symbol button, we're going to click that and just make a box about yay big. So this is what we're going to do is we're going to put the microcontroller sheet inside this sheet. So if we double click it, so double click the green rectangle. If you double click like the file name or the designator, you'll get the properties of those like text boxes. We actually want to double click the box itself. And then under source here, there's file name. So if we click these 3 dots, it'll bring up all of the schematics currently in our project. So we can just click the microcontroller one and add that. So now this is called microcontroller schematic document. And we want to get all of these ports that we defined into our into this, so we can interface from it from the outside. So this is probably like the most steps thing that I'll have you go through. But if you right click on this and go to part actions, no, it's been a while since I've done this.
Will, you can do it if you just right click on like a white space.
Yeah.
And then go to sheet actions, and then go create sheet symbol from sheet, and then click microcontroller. Yeah.
And it's got all the things. Oh, that's a much better way of doing it. Okay. Ignore what I did. So we're going to right click on a void and go to sheet actions, create sheet symbol from sheet, click microcontroller and click OK. And now we've got this block here that has all of the ports on it that we want. Now they're sort of a bit out of order from what we want, so we're going to move them around a bit. Did anyone miss that step? Was that fast, slow enough for everyone? Oh, good, cool. So we'll move CAN, RX, and TX to the right. And we'll move the I2C and the wake pins to the other side. So now, instead of having to worry about, the programming connector, the crystal oscillator, all these like miscellaneous capacitors, all we care about really is that the microcontroller has a CAN interface and an I2C and this GPIO interface. Wonderful. So now you're just going to do that to the rest of them. You can also see now that when you've added that and saved it, your schematic sheets now get this like hierarchical structure. So you can see on the finished product here, we've got the top sheet and then the microcontroller, CAN transceiver, and the sensor, all as like sub-modules. So in principle, if you wanted 2 microcontrollers, you could copy and paste this and call this one new microcontroller 2. And then when you import it into your PCB, you will have 2 of the exact same microcontrollers with all of the supporting hardware there to do, but we're not going to do that. All right. Next up, we'll do the linear regulator. So this happens a lot on the Rover. We've got 5 volts going to a lot of places, but these microcontrollers here are 3.3 volts. So we're going to get the linear regulator, which is this part here. So that's in the chat. And we'll open up the data sheet as well. That'll do. So on the data sheet, if you go to typical application, which is page 21, you can see for, wait, this is, where is it? Oh yeah. So all right, here we go. So no, this isn't what I want. Turns out these can be used in a lot of different ways. Didn't know that. All right. So we'll just stick with, so this, we've got the 3.3 volt version. So we'll just stick with the output capacitors and the input capacitors that are here. Oh, here you go, for other fixed output voltages. So we want 10 microfarad on the output and 100 nanofarad on the input. So we will paste this into our components, and someone has very nicely already made it, me. And we're just going to put this on the top sheet because there's no like inputs or outputs from this because everything is all just power based. So we'll grab our 100 nanofarad capacitor, also known as a 0.1 microfarad. So this is the exact same one that we used before, which is great. If you can reduce the number of different part numbers you use, then you save us a lot of headache in inventorying all these different parts. So we're going to connect that up to ground, and we're also going to connect up this 5 volts. Now, instead of calling it +5, on the other sheet, I used 3V3 for the thing. So I'm going to call this 5 volt just to be consistent. And then same over here, we need a 10 microfarad capacitor. So we'll just use the same tantalum one from before. It might be ideal to use a different type of capacitor here, but that'll probably do. And again, I'm just going to hide the part number because I don't really care. All right, and then we connect that up, and we connect up ground, and we also need to connect the ground pin of the linear regulator. So all this does is step down 5 volts to 3.3 volts, and now we can use that 3.3 volts anywhere on our board. It's probably a good time to talk about the scope of different connections. So before, when we were using these net labels only connect to each other on one sheet. So if you've got PGC here, and then on your top sheet, you have another pin called PGC, they're not going to connect unless you do it through this microcontroller or you change the settings of your schematic so they do connect. But I wouldn't recommend doing the latter because you'll confuse people. So yeah, basically net labels are local to the sheet. Ports are like global through their connectivity. And these power things are global across your entire project. So anything that has this 5 volt will connect to this, which makes sense sort of intuitively. Cool. All right. So the linear reg's done. Now let's do the CAN transceiver. So we're going to go new schematic. And again, we'll save it and call it CAN transceiver. And get our CAN IC. So this is a different chip to what we used in the previous workshop, because like the one that was already on YouTube, because that one that's on YouTube has gone out of stock because of the silicon shortage. So grab that CAN transceiver and chuck it in. And if we have a look at the data sheet again, go to the TI site. So it's always worth having a look at the data sheet of the components you're going to use, because there's a lot of information in here, and you can't really make assumptions. If you make assumptions, you might make a mistake. So the best thing is like a typical application schematic. So if we go to page 20 here, so this is a typical application for a 5 volt microcontroller, and here's a typical application for a 3 volt microcontroller, which is what we're using. So you can see here they've got the 3 volt voltage regulator and their 3 volt microcontroller. And then they've got RX and TX connected. They've got 3.3 volts connected to VRXD, ground connected, and then the CAN high, CAN low, and then also 5 volts connected to VCC. So to give you some background, because this is a 3.3 volt microcontroller, it can only tolerate 3.3 volt signals. So we have to communicate between the microcontroller and the CAN transceiver at 3.3 volts. However, CAN uses 5 volt signaling. So the signal differences between CAN high and CAN low are going to be 5 volts. So we still need this 5 volts to be able to generate that difference, but we need to be able to talk to the microcontroller at 3.3 volts. There's also this S pin, which I'm not sure what it does. Might just ignore that. If you're interested, you can figure out what it's meant to do. I don't think it's necessary. So we're going to start by connecting ground to ground and connecting VCC to 5 volts. All right. And then we're going to connect CAN high and CAN low to ports, bidirectional ports. So CAN high, CAN low. And we'll change these. A little tip for you as well. If you want to like change a parameter for multiple things, you can select one and either like drag to select or select one and hold shift and select the other. And then you can change the IO type for both of them, and then they'll both update. So that's a little handy trick. Okay, so that's connected. And then we also want RXD. So we'll call this CAN RX so that we're consistent with what we called it on the other sheets. And we'll call this one CAN TX. So CAN TX is now an input to this sheet, and CAN RX is an output from this sheet back to the microcontroller. So those are connected. And then finally, VRXD is the voltage level of the RX pin so that we don't explode our microcontroller. And this needed to be 3.3 volts. Cool. Give everyone a minute to finish that up. Anyone stuck anywhere? Cool. All right, so back to the top sheet, and we'll go right click, sheet actions, create symbol from sheet, and this time we'll get our CAN transceiver. Bam, there it is. So we can sort of logically lay this out. We're going to put a connector over here that takes the CAN high and CAN low signals, and we'll put this in line with the microcontroller so that these can talk. And while we're here, we might as well connect up the CAN RX and TX pins. So try those. And yeah, at any time, if your cursor's like stuck using a tool, if you just like hit escape, like if you just spam it, it'll exit out of the tool and you'll be back to a normal mouse cursor. All right, so that's CAN done. Excellent. Now we'll do some connectors. So this here is an EP 2.5 connector. So if you punch that in, or if you type in economy power 2.5, you'll get the same part. We've only got the one at the moment, but I assure you there will be more soon. So this is a typical connector we use all the time in the Rover, and we're just going to get our power input from this. So we'll put a +5 on pin 1, and remember we got to rename this to 5 volts to be consistent with what we're doing elsewhere, and then also a ground. I'm not sure, but there might be a way to like reconfigure what these default ones are, because like we never really use the -5 volts power port because it's not something we do. But yeah, anyway, so that's the power done. And like what we do with a lot of the ARM electronics, we're going to use an RJ45 connector or like an Ethernet connector for the CAN lines. So again, just punch in that, and that's what it looks like. So you can see we've got 8 pairs. So we typically, I think it's pair 1 and 2 we use. Yeah, pair 1 and 2, so high then low. So just connect CAN high to pin 1 and CAN low to pin 2. If you come to the ARM electronics workshop on Wednesday, I'll explain what all the other pairs are used for. But essentially it's power and also the RS-485 bus. These two S1 and S2 pins down here, these are like the shielding, so like the metal housing of the connector. You can see there's like 2 little metal tabs here. So you can leave those unconnected if you want, or you can connect them to ground. I think for like noise reasons, it's better to connect them to ground, but to be honest, I don't think it really matters. So we might as well do that. All right, and then once again, we'll go new schematic, and we'll add one in. We'll just call it sensor. So this is for the CCS 811 sensor. So if you put that into your component search, you should get it. One thing that's kind of interesting is if you search, because this is often used in like SparkFun and like Adafruit, like little packages, like little boards with pin headers. When you search for this component, you'll get like all of those first before you actually get the IC, but you can dig down and find one. And also like this is not stocked at anywhere good. I don't know what J3 is, but it's probably not a particularly reputable place. Immediately request for quote. So when you're looking at Octopart, which is this site here, you can see like these Ethernet connectors, lots of stock at RS and at DigiKey and at Element 14 and Mauser. So they're the main ones we use. Most of the other ones on here, we probably won't use very often. Sometimes we buy stuff directly from Texas Instruments or from Microchip if we need to. All right, so this is the data sheet for the CCS 811. And if we go to, so it's quite a substantial document, like 30 pages. And where is the table of contents? Did I skip it? Oh, here we go. So on page 12, there's a recommended application circuit. So you can see here, there's this GPIO pin going to the N-Wake, and then the SDA and SCL pins. And here they also have pull-ups on the SCL and SDA pins. depending on what you're doing, it might be worth placing these on your schematic. You don't necessarily have to place the resistors when you assemble the board. Most microcontrollers will have internal pull-ups on the STL and SDA lines. But if it doesn't, then you're going to get nothing on your I2C lines. So worth checking, or worst case, just placing them anyway in your schematic. And then when you assemble it, you don't have to put them on, and it won't really break anything. All right, so here we are. We'll get 2 ports again, 3 ports actually. So we've got SCL, SDA, SDA, and NWake. And we'll just connect these up like so. Now we've got VDD. Now what voltage was VDD? If we search in here, supply voltage, 1.8 to 3.6 volts. Okay, so we can supply it with 3.3 and that'll work fine. So we'll get our 3V3 and connect that. Yeah, so this page of, here we go, this page of the schematic is usually quite helpful. So it has all the pin numbers and what the pins are and what they do. And it often gives you some tips on how to do it. So here it's supply voltage. This one called EP is the exposed pad. So that's like this middle pad on the IC here. So that one we connect to ground. So we'll do that. And it also says pins 4 and 5 must be connected together. So the PWM and the sense pins. So we'll just connect those together. Now in reset, it's an active low input and it's pulled up to VDD by default. So what that means is if we pull this to ground, it'll reset, it'll like reboot the chip. We don't really want it to do that, but if you wanted to have control over that, you could hook this up to a separate pin on your microcontroller, and then you could reset it by the microcontroller, or you could have like a button that resets it if you wanted to. And same with like this int pin. This is an interrupt pin, so when the measurement's finished, it'll pull this low. Again, we don't really care about that, but depending on your feature, you might want that. Everything else here, I'm pretty sure we can leave unconnected. So we'll just hit save. And again, we'll change our SCL and SDA pins to be bidirectional and our NWake pin to be an input. Save that. Cool. All right, back to the top sheet and we'll import this. So right click, sheet actions, create sheet symbol from sheet and whack that down. So we'll just move these around to the other side. Oops. Sometimes the ports can be a little fiddly to grab, but sort of knack. And then we'll connect those up all together. So now we've got this nice logical flow block diagram. There's all this information in the sensor sheet and the microcontroller sheet and the CAN transceiver sheet with all their resistors and capacitors and programming connectors, but we don't really care about that at a high level. We can just connect them together and you can immediately glance at this block diagram and say, okay, the microcontroller talks with I2C to the sensor and the microcontroller sends CAN messages over the Ethernet connector. Cool, makes sense. So yeah, in principle, we would power this board from the 5 volts here, and it would send messages over the CAN high and low pins. If you want to, you can watch the PIC workshop from last year. That workshop goes through this exact board and how to program it to do what you want. All right, so we're done with the schematic, I believe. I don't think there's anything critical I missed. There's no components I haven't used. Cool. So now we're going to make our PCB. So again, either right click, add new to project PCB, or file new PCB.
Sorry.
Yep.
For the CAN transceiver, I placed the ports around the chip, but I don't remember connecting them. Ah, right, those connections.
Yep.
Yeah.
So when we were on the top sheet, when we imported it, it goes here. Yeah.
Yep. And so let's say I accidentally set CAN H or sorry, CAN TX and RX as the wrong types. And then I imported those into the top sheet, but then I changed them in the schematic for the CAN transceiver. How
Yep.
do I update that on the top sheet?
Yep. So you can either like delete it and delete this and redo it, or you can go right click and go sheet symbol actions, synchronize sheet entries and ports. Actually, let me just do that. I'll change this to be output and this to be input. And you can see you've got like an error here because these are both outputs and they're driving each other, and it's like, okay, something weird's going on. Sheet symbol actions, synchronize sheet entries and ports. And you can see that now there's a CAN. So this is representing what's in the sheet symbol, and this is representing what's in the subsheet. So you can see we've got CAN RX as an input and CAN RX as an output. So if you select both of those, these buttons here will, so this one will turn the output into an input, which is not what we want. We want to change the input to an output. So we click that one. And then we select those two again and click this one again. And now they're the correct way around. Does that make sense?
Yep.
Yep, cool. And yeah, also if you like add new ports to your microcontroller, for example, and you need to bring those onto this subsheet, you do the same thing. You go synchronize, sheet symbol actions, synchronize. Nope, that's not it. Sheet symbol actions. Oh, sorry, it's saying all symbols are matched. But if you had more, you could add them in that way. All right, so you've got your new PCB. So again, file, new PCB. So it's just this big black square. If you press 3, you'll get this like 3D view. So you can pan around with right click or same controls. And if you want to like rotate, the rotating is a bit weird. You have to hold shift and then right click on this like sphere to rotate. So if you press 2, you'll go back to normal view. And if you press 1, you'll go to this layer stack like view. That's like a board design view. So the first thing we're going to do is we're going to import all the stuff from our schematics into the PCB. So the way we do this is we go to design and we go import changes from project PCB. If you hit update schematics, you'll end up undoing everything. What it'll do is it'll take what's on the PCB and it'll update the schematics to match, which I never ever recommend doing. Always change your schematics and then update the PCB. So design import changes from PCB. Sorry. First thing you got to do is save it. So we'll just call this like call this gas sensor board. So save it so that it's got a name, and now you can import changes. And I forgot a step. Okay, so you can see now that all of these are basically all the changes it'll do. So it'll import all these capacitors and connectors and resistors and stuff. It'll import all of these nets that connect them together. So nets is just like, like a node or a trace. It'll add some classes for components, and it'll add all these rooms. But you'll see that they still have question marks on them. And we actually, at this point, we want to have unique designators for anything because it'll get confused. So if we go back to one of the schematics, it doesn't matter which one. And we go design, tools. Yeah, tools, annotation, and then annotate schematics. And then if you click, so it's got, this menu is kind of confusing, but essentially if all the schematic sheets are ticked here and all of the options here are ticked, so this is just like all the designators. If we go update changes list, it'll say changes made, 17 changes were made. And then we go accept changes, create engineering change order. And then it will tell you, here's all the changes I'm going to do. So I'm going to change this C to C1 through to C7, J1 to 3, R1 to 2, blah, blah. The reason why I prefer doing it this way is that it ensures that all of your capacitors and stuff are sequential. Because often you'll have to like you'll name one of them R1, and then you'll be like, and you might go up to R6, and then you'll come back later and you'll be like, which resistor was I up to? Was I up to 7? I can't remember. So this just does it automatically at the end. So then just go through and save all of your sheets. And you can see when we did that, it actually ran a check on our schematic, and it's given us some errors. So one of them is this floating input pins error. So this is this S pin, and one of them, and there's another floating pins error on the sensor reset pin. Now we looked at the data sheet before. The reset pin was actually internally pulled up, so it's not a problem that it's floating. So you've sort of got two options at this point. You could go back into the component and change the type of this pin so it's not an input, so it's like a passive. Or we can just place a no error check designation on it. So only place these if you actually know that it's fine. But if you right click on the parameter set thing and go generic no ERC and place that on the reset pin, it will make the error go away. And we'll just do the same. We'll do the same for the CAN transceiver. I haven't had time to check what this actually does, but just so it stops complaining. And then to run that, again, you go validate PCB project, and now those errors are gone. We do have some warnings left. So for example, it's saying that net R2 side 2 has no driving source. So basically what that's saying is that because this is an input pin and there's nothing like active on here, it's just like resistors going to the connector. It's not sure if that's correct. It is fine in this case because all the active stuff is happening in the PIC kit, which we plug in. But it's good that it's raised a warning. And here we've got that the IO pin. So this is an input output pin, but it's connected to just an output pin. Now that's, again, it's fine that that's a warning, but you would want to, but it's good that it's checked and it's made sure. Yeah, Jonathan?
How did you do the validate thing again?
Yep, so if you go project validate PCB. So yeah, if you wanted to, you could go through and change. You could add no ERC checks to all of these, but they're just warnings, so it's probably okay. All right.
I don't see the errors.
It's in the messages panel, Alex.
Yeah, so if you don't have the messages panel, if you go panels messages, it might come up.
Right, yeah.
Cool. All right. So we've got this blank PCB, and we're going to import our changes now that we have designators. So we'll go design, import changes. And now everything has good designators. And all we'll do is just click this execute changes button. It might take a couple of seconds to run. But it's got, so you can see here, it's done all the checks and it's got all the green ticks that it's done and there's no problems. And you can see here that all our components are now off the PCB, but they're here. And they're all in these like little red rooms. So these are called rooms. And basically based on the structure of your subsheets, the sensors will go into rooms like that. So for example, the PIC microcontroller subsheet, we've got the programming connector, the crystal here, the PIC itself, and then some of the other stuff. And then here's the top sheet. So we've got the linear reg, the power input, and the CAN Ethernet connector. Cool. So at this point, we're just gonna like drag. So if you click on the rooms itself, it'll drag all the objects in the room as one big group. Just drag them onto the board. Now, one thing I've just realized is that this sensor here should have a decoupling capacitor or a 0.1 microfarad capacitor. So what we're going to do is we're going to go back to the sensor page and we're just going to grab a 0.1 microfarad and we'll just place that there and we'll connect it up here and connect it to ground. And then again, this is no longer, this doesn't have a designator here. So can I do it here? Don't think so. So again, we'll just go project, no, what is it? Tools, annotation, annotate schematic, update change list, accept changes, execute. Doesn't really matter if you didn't do that. You'll just have a C question mark. But so we've updated the schematic, but the component isn't here yet. So again, we have to go back to design and import changes and then execute that. And now there's a capacitor here and it's complaining because it's not in the room that it's meant to be in. So that can happen. So when you import stuff, sometimes the rooms can get a little bit wonky. But now it's happy. Now you'll see that a lot of our components have, I'm going to get rid of the messages because it's taking a lot of space. A lot of the components have like big like green pads on them. Kind of like what's going on there? Why are some of them red and some of them green? These greens indicate there's a problem. And if you zoom right in, it's a bit hard to see, but you'll see that this says, there's these two little arrows and it says less than 10 mil. So this is imperial mils, so less than 10 thousandths of an inch. And what it's saying there is that the space between these pads is too small. But too small for what is the question. And the answer is it's not defined properly yet. And the reason is we need to import our design rules. So the design rules, which I think are touched on in the background reading, basically the design rules are set to the specifications of our manufacturer, so JLC-PCB, and it's so that we don't exceed the like capabilities of JLC-PCB when they're designing boards. So we don't make traces that are too thin or holes that are too small or put components too close together and stuff like that. So the way that we import the design rules is you get the design rule file. So if you go back to Slack, the useful info thread has the 2-layer board.rule file. I wonder, can I put that in the Zoom chat? I can. No, I can't. I can only do Google Docs. So yeah, grab that and just download it. Let me know if you can't find it or whatever. And we go to design rules. And you get, so these are all the rules here. So you can go in and play with these if you want to. But what we're going to do is right click on design rules at the very top and go import rules. And then we're just going to select all of these. So make sure the first one's selected, scroll right to the bottom and hit shift and select the bottom one so that they're all selected. Hit OK. Go find the file and import that. And they'll come up saying clear existing rules prior to import. We don't care about the old rules, so yes. And now all the rules have been updated and a lot of those errors are gone, including all the rooms for some reason. Don't know why.
So
anyway,
where do we find the design? Where do we find like how can we change it again? Sorry, just for
the file itself, or how do you change it? How do you import it?
How do you change it? Sorry.
So design rules.
Yeah.
Right click on design rules at the top left here and go import.
Yep.
And then make sure the top one's selected. Scroll to the bottom, hold shift and select the bottom one so that they're all selected. Hit OK, and then select the file, hit open, and then hit yes.
Gotcha. Thank you.
Cool. All right. So I don't know where all of the rooms went, but all of our errors are gone, which is good. Now, one thing that's quite important when you're laying out your board is that you kind of keep the components that were next to each other. And I've just realized that we need another decoupling capacitor on the CAN transceiver. But anyway, yeah, you can see, so this is the PIC and all the stuff on the PIC. This is the CAN transceiver, the sensor and its capacitor, and then here's the linear reg and its capacitors here. So basically all the routing is like connecting the dots. It's not particularly hard. There are sometimes you've got to like have some considerations about how thick your traces are if you're doing a lot of current, or the exact like impedance of your traces if you're doing really high speed signaling. But for the most part, it's pretty straightforward. So we're just going to have a look to start with at all the pick stuff. So I'll grab the pick and we'll start with like the crystal here. So you can see as I like drag the crystal around, it's sort of connecting the lines to like the closest pad that is relevant. But essentially we need to connect the OSC, the oscillator pins, to the pick and also the capacitors. So what I'm going to do is I'm going to rotate the crystal like this, and I'll put one capacitor. So it's worth always just checking what the pins are actually doing. So I'll put one capacitor here and the other capacitor over here. And you might want to move the designators around. And you can see here that the wires are crossing over, so I need to rotate this. So same as in the schematic, you just hit space to rotate when you're holding it. Cool, so that's in. And yeah, so again, like in the schematic, it's all about sort of, in the schematic, it's all about communicating to the engineer that's gonna, make future changes or has to debug your circuit, what's going on. On the PCB, it's all about communicating to the person that's assembling your board, what's going on, also the person that's got to fix your board when there's problems, and just like, the general user of the board, where do I plug stuff in? So it's very good to make extensive use of the silkscreen layers that was in the pre-reading. So this top overlay layer, you can put a lot of notes on that for when people are looking at the board, more than just the actual designators. And if you want to, for example, say we had like an array of like 10.1 microfarad capacitors, and I didn't want to have like C1, C2, C3, C4, C5, C6, etc. next to them. You could actually just hide the designators from all of those and then put a note saying these are all 0.1 microfarad instead. And that would demonstrate the same information to the engineer. Anyway, so we've got our crystal oscillator roughly laid out here. And just like the schematic, if we press Control W, we get the routing tool. You can also click this button here, the interactively route connections. So we'll click on our OSC1 pad and just click there, and that's now connected. And we'll click on our OSC2 pad, and you can see it's kind of smart about how it wiggles around components. So it's pretty clever. Sometimes it can be a little bit annoying. And again, you can press spacebar to like change how it elbows. So we're going to make it run like that. So it's sort of next to the other one. And then we'll also connect up the capacitor. Now, okay. Now we're going to leave the ground pads because we can do a trick at the end called a polygon pour to connect all the grounds, which helps with EMI. But it's sort of annoying having these grounds going everywhere because like ground's the most common net, right? It's on basically everything. So we're going to hide these lines. These are called connections. So if we go to View Connections and then Hide Net, we can then just click on Ground, and now all the grounds are hidden. You can also, if you've got a really big board with like thousands of connections, you can hide all of the nets and then just show. You could go Connections, Show Component Nets, and then click on like the pick, and that would just show the things that the pick connects to. So that can be helpful as well. All right, next up we'll do.
Sorry.
Yep.
What did we do with the grounds?
So go View Connections, Hide Net, and then click on one of the ground pads, and it will hide all the connections for the ground.
Oh wow, cool. Thanks.
This helps with the clutter. You don't have to do that, but it sort of makes it clear what you have to route, because the ground pins you typically just do with a polygon pour. Yep.
And also, just quickly, I added the decoupling capacitor a long time ago, but I wasn't able to rename the designators.
Oh yeah, do you want to do that again?
Yes, please.
Yep. So if you go to a schematic and go Design, Tools, Annotation, Annotate Schematic.
Yeah.
And then go Update Changes List, and then click Accept Changes, and then click OK. Did that work?
Yes, it did. Thank you.
Cool. Now you will have to import changes again from your schematic to your board.
Mm-hmm.
Just
Um,
quickly,
yep.
how do you rotate components in the PCB?
So it's the same as schematic. So you just like click and drag it and then press spacebar.
Oh, so it's whilst to drag it, because I was like clicking on it and I was wondering why.
Yeah. So
yeah.
yeah, it's just, yeah, get into that habit. It'll sometimes when you click on a component and press spacebar, it'll actually rotate it about the origin. And so like this part will end up like over here. I think if you select multiple things. Yeah. Anyway.
Awesome. Thank you.
So yeah, it's worth sort of putting a bit of thought into how your silk screen is laid out. I'm not going to do it in detail here because we just don't have time. But yeah. Now one thing is, for example, these decoupling capacitors, so C345, if we look back to our microcontroller sheet, these had to be, and if you look on the data sheet of the PIC, it specifies that these have to be like as close as possible to the chip, and that's very common. So even though like C5 here is saying, oh yeah, I can connect to this connector, right? Because this is 3.3 volts in ground. That's not what its purpose is. Its purpose is to connect over here to the microcontroller. So we'll put that there, and we'll grab the other one as well. That one goes up here. Now the other thing is because AVSS, which is pin 27, is just connected to ground, the lines will connect it. Like if I drag it over here, it'll say, oh yeah, I can connect to pin 19 if you want, but we actually want it to connect directly to pin 27 because that's good for basically the AVSS is used for the ADC pins. So and it's got some special noise filtering. Anyway, I won't go into too much detail, but that's that. And then we've got this other capacitor for the processor itself. One thing, if we go back into if you press 3, you'll go back into 3D view. You can see all the models for the components as well. You can see that this capacitor is actually like kind of tall. So if you were to try and hand solder this, and you did the PIC, and you did the capacitor before you did the PIC, it's actually going to be really hard to get the soldering iron into these pins. So it might be smart to sort of push this away slightly just to give yourself a bit more room. And I might put the designator on the inside there. Yeah. All right. And then we've just got the programming connector to lay out. So this has the 2 resistors. So I can put one there and the other one goes something like that. Now, one thing I find helpful is that by default, the designators are quite large, and you can make them smaller if you want to. There is a minimum size, but the quick way to select them all is this selection filter here. If you, this will, for example, if I turn components off, if I click on a component, it won't actually like select it. But if I click like here, I'm clicking on the pad of a component, and it is selecting it because pads is still enabled. If I turn them all off and then turn on text and then Control A, all of the designators will get selected. So I can change this. I think like 40 mil height is okay, and like 6 mil stroke width. Yeah, so that's a bit smaller. So it might be a little bit easier to lay them out. Now the designators are like, you can definitely go smaller than that, but there is a minimum size that they'll print. So just be careful. And then don't forget to turn on all of your things again. Cool. All right. So now that this is all kind of roughly laid out, I might move the connector up, maybe up here. Something like that. we can route everything together. So just Control W to get your routing tool, and it's just connect the dots. So you can follow the lines. When you click on the net, it'll show you where it needs to go to. So this is a good example. So this PGD line has to go under, like, past these traces. So if you wanted to, you could route around like this. But what you can also do is use what's called a via. So if you did the pre-reading, there's 2 layers to boards. So we can actually scoot underneath these traces by using the bottom layer. So the way to do that, the easiest way is to hold down, while you're routing, hold down Control Shift and scroll wheel up just once. And you can see down the bottom of my screen where so you can see I'm toggling between top layer and bottom layer. And you can see there's a via appearing where my mouse is. So now I'm on the bottom layer. I can let go of Control Shift. And now I'm routing underneath the trace on the bottom layer. And then I can do the exact same thing. I can Control Shift, scroll wheel up. And now I'm back on the top layer and I can route that in. So you'll use this extensively, particularly in more complicated boards. And yeah, it's pretty good. So get used to that. And yeah, if you want to change layers in general, is Control Shift scroll wheel is the easy way. When you're routing, so you can see at the moment, because I'm not routing, I can change to any layer, like mechanical 15, whatever that is. But if you're routing, your options get reduced down to just your 2 PCB layers. If you're doing a 4-layer board, there'd be four layers there. So I'm going to do the same thing. I'm going to route onto the bottom layer here and scoot underneath the whole IC, and then route in like that. And then what's this pin? This is 3.3 volts. So, and then yeah, once you've like routed traces, you can still kind of drag them around and maneuver them a bit if you need to. So this 3.3 volt trace, maybe I'll go underneath here to get to here, something like that. With power traces, particularly for like higher current devices, like, you know, hundreds of milliamps or 1 amp or so, you might want to use some slightly thicker traces than these. These are just the default thickness. A couple other things. If at the moment all of the like dimensions are in imperial mils, if you want to, you can just like click on a blank spot of the PCB and open the properties tab. And if you scroll down to the bottom, there's this units thing, and you can toggle between millimeters and mils. So I think if you, yeah, so I'm going to change it to millimeters so that everything's how I want it, and continue routing. So it's going to route 3.3 volt like that. Okay. Anyone stuck with the pick at all? So just as like, oh yeah, go.
I'm just a few components behind.
Yep.
So the C5, C3, and C4. Yeah. Okay.
Cool. All right. So that's basically the pick routed. Now you'd probably want to spend a bit more time sort of getting the layout right. Like some of these traces probably don't have to jump underneath the layers if I spend a bit more time thinking about it. But you can see that we've got these lines here going to the sensor, and we've got these lines here going to the CAN transceiver. So it might make sense if we put the CAN transceiver sort of above the sensor, or if we move the sensor like over here and maybe we rotate this whole thing. So remember, you can press space to rotate. Now the lines sort of line up a bit better. So put the sensor here, and again we'll just put the capacitor on the side here because it needs to connect between 3.3 volts and ground. And yeah, we might bring it a little closer, and we'll just route between here. So you can see that the I2C, I think this is the N-wake pin, crosses over the other 2 pins. So we might route these two first. Let's sort of smudge that over a bit. And then, oh no, this one crosses over too. Okay, so we'll jump to the other layer and get out that way. And what about this one? Okay, so we're sort of a bit cramped in here. So I might move this capacitor to the other way so that there's a bit more space in here. And again, we've got to jump through. So yeah, the routing's pretty smart. It'll like nudge things out of the way if there's not enough space. But you can see that this is kind of messy. So I might sort of move this via over to the side a bit so these can be straighter. And maybe move that one over a bit and get that to be straight. And then fix that up as well. Yeah, not perfect, but you know, it'll work for today. And then I'll route my power in from around here. I might just jump underneath here to there and connect the pad to the capacitor as well. And then I've also got to connect, remember pins 4 and 5 on the IC have to be connected together. All right, I won't fix it because probably running a little low on time, but the capacitor here, sorry, the CAN transceiver here needs a capacitor on the VCC, the 5-volt input. I forgot it. So if you were designing this for yourself, you'd add that in, but it'll work for today. And then, so we need to connect the CAN pins. One thing you can do as well, if you control click on a pad, it will show you like, it'll highlight all the other pads that it connects to. And then if you just control click on empty space, it'll clear it. So I might route this down like here and then run these through like that. Okay. And then let's put our CAN connector here, our power input here. And we might put the linear reg stuff up here. So the linear reg is pretty simple. It's just got one large capacitor on the output and one smaller capacitor on the input. So maybe something like that. Just route those together. So these traces you might want to make a bit thicker. So while you're routing, if you press tab, it'll sort of bring up this pause thing and you can change the width. So we might change it to be, say, 1 millimeter. And now it's a bit thicker. And maybe we'll rotate the whole thing like that. So it sort of fits in like that 1 millimeter as well. Connect it up to our power. And if you want to change a net afterwards, you can either like select it and remove it and reroute it at the new thickness, or you can double click it and change the thickness there. All right, we're running out of lines to connect here. So it's good. So we've got to connect our CAN lines to the output. So I'm going to shrink this back down again to maybe 0.4. So that one goes there, and this one goes maybe like that. I might move that down and kind of wiggling all over the shop here. There we go. Yep. And then I've got to connect 5 volts. So we'll just get that directly from the input. And this isn't a high current trace, so probably be okay at 0.4 millimeters. And then lastly, we've got 3.3 volts here. Again, I'll make that smaller. And 3.3 volts to the connector like that. So now we don't have any more gray lines. And if we look in 3D view, we've got a nice looking board here. And we've got so the Ethernet connector there and our power input and all that. So if you were doing this for real, you might I would highly recommend spending a lot more time in the component layout stage, making sure everything sort of fits together nicely and where all the traces go make sense. But we've done a reasonable job here, but there's sort of a big space in the middle here, up the top. So yeah, that's routing done. Now we're gonna change the board shape. Is anyone stuck anywhere before I start that? Cool. All right. So we're gonna press 1 to go into the board. I don't know what they call this mode, like board layout mode or something. And you can see all our options have changed. Oh, there you go, board planning mode. And under design, we can now all these board shape options. So we can redefine board shape, which means we actually like click in points to redraw a new shape, or we can edit board shape. Edit's probably the one we want. And you can see now there's all these like sliders, so we can drag down the board to sort of suit what we want. So now it's a bit smaller, sort of sits with the components a bit better. But we might actually want, you know, we need to mount this to something. So we probably want some mounting holes. So I'm actually going to go back to board planning mode and make it slightly bigger. And then I'm going to insert, so you can insert like a via or a pad. It doesn't matter really which one, they're sort of the same thing. No net is fine. And we're going to set the diameter to be 3.2 millimeters. Oops, that's not right. We're going to set the hole size to be 3.2 millimeters. So this is basically, if we now look at our board, now there's a hole in our board. Now we use 3.2 millimeters because that's an M3 bolt clearance fit if you're playing along, if you're a mechanical head. And you can see we kind of, because this is a sort of a mechanical part, we want to be reasonably precise with how it's laid out. So we can change our snap grid so that it's easier to get accurate. So if you press Control G, this will open up the grid editor. And we can change the snap grid to be 1 millimeter. And now you can see the dots on the grid have changed, and now the hole snaps much easier to the to there. Now to copy and paste stuff in the PCB editor, it's a little bit different to other things you might have used. So like selecting here, and when I hit Control C, it brings up this cross. Now what this cross does is, although I've got this component selected, so this is the component that I'm copying, but I can actually like define where I'm copying relative to. So if I click on the edge here, when I then Control V to paste, it'll be relative to my cursor out here. So that's just something to be aware of. So, but if you just like hover over the center of it, you'll get the like circle on your crosshair, and that means you're on the center. So that'll do. So I'll put one of those in each corner. You can see that my board isn't actually like on a millimeter grid. So again, I'm going to go back to press 1 to go to board planning mode, and then edit board shape. And I'll snap that out to sort of the next closest millimeter. And let's have a look at our holes. I don't think they're lined up properly. So let me get them equidistant from the edges. That looks better. So now if you hand this to a mechanical engineer, once you've made it, they can actually mount it down properly, which is good. And yeah, you might want to consider things like how the cap, the head of this bolt might interfere with this connector potentially, just little things like that. Cool. So the last thing, once we've like finished all of our design, we need to verify that it passes all those rules that we imported before. So if we go tools and then design rule check, this will bring up these options. If we just click run design rule check, it'll run all the rules. And you can see, oh no, we've got a big problem. There's all of these unrouted net constraints and minimum solder mask sliver constraints. Now, if you're clever, you probably realized that we forgot to route all the ground stuff. And that's because we were going to do a ground pour and I forgot. So the way you do a polygon pour is with this icon here, the one next to the VIA one. And it's pretty easy to use. Basically, you just, in this case, because we're just going to route ground across the entire board, you just select the 4 corners of your board. And then once you've finished, it'll still be like able to click more. If you just hit escape, it'll define it. So now we've got a polygon pour, but it's still not connected to the grounds. So you can see there's like copper isolation around it. That's because if we click on it and look at the properties, the net here is unassigned. So it says no net. So we can either pick it from the list or we can use the eyedropper and go find a ground like that one and click it. And now it's assigned to the net, but it's gone like green. And what the green means is that it's been modified. You can see here, polygon not poured. So you can either click repour here or here, and it's going to repour it. And now you can see all of our ground pins now have this little like cross hatch across them, connecting it to the ground plane. So even this center one of the IC there, they're all connected to ground. The reason why they use this like cross hatch symbol and that's actually how the copper will be laid out. It's because it gives thermal relief. So it's what's called a thermal relief. So when you're soldering it by hand, it means that less heat can be sapped out of the pad while you're soldering it. So it gets up to temperature easier. So it'll melt faster. Whereas if you don't have that, it essentially has to heat up the entire ground plane in order to melt the solder on the pad, which can take a while. All right, so we've still got all of these symbols here. I think if you go view, I can't remember. There's a way to hide all of these, but if we just run the design rule check again, so we go tools, design rule check, run design rule check. You can see we've still got 52 violations, but the unrouted net constraints are now only 4, which is interesting. So where is that coming from? So, it's these. Okay, hang on. Sorry, is that fix it? No. Okay. I think instead of using, well, actually, okay, what you can do, these holes, if you just assign these to be ground as well, which is usually a good thing to do, and then run your design rules. Oh, wait. Yeah, if you run your design rules, it'll still give the error because we haven't re-poured the ground plane. And now you can see these holes are now connected to the ground plane. So now if we run the design rules, sorry, it's a bit all over the shop. Cool. We now have still 52 violations, but all of the unrouted net constraints are gone. And we've got 4 minimum annular ring constraints and 44 minimum solder mask sliver constraints, and 4 net antenna constraints. So to give you a bit of background, basically the minimum solder mask sliver is talking about the IC down here. Now this is a QFN package, so it's quite tight and the room between the pads here is very small. If you wanted to fix this, you would go back into the component and edit it and reduce the thickness of the solder mask. So the solder mask is basically, it's a bit hard to see, but you can see how like this is the pad here, and you can see how the solder mask, the green bit, is like padded out around it. So you could decrease that padding so that it so that the sliver of solder mask is not too thin. Basically, JLC will do their best at printing it, but it may sort of peel off, which can make which can make soldering a bit annoying because it can make it easier to short 2 pins together. So yeah, if we were going to fix this, we'd go through and change the component. Or you can just sort of ignore it if you know that it's okay. This minimum annular ring stuff, yeah, okay, it's because I've done these holes in a bit of a weird way. How I generally recommend you do the mechanical design of your board is actually design it in SolidWorks and use the MCAD co-designer utility, which lets you kind of move boards between Altium and SolidWorks. And then you can actually define these holes as proper holes in the board. Basically, these holes are causing us grief because the ring of copper around them is too small. So if we make the diameter like 3.5, then there's actually copper around it, and it should be less angry. So I'll just select all of them and make them 3.5. Oops. And cool. Yeah. Now it's still complaining about net antennae. Basically, net antennae means that there's like a net that runs, like say you've got a component here and it just runs to nowhere. And basically, if you've got a signal on this, it'll resonate like an antenna. So the reason why it's complaining about this is we've actually got a via in 3D, right? So this is an antenna going into the PCB in some respects. It's not, because the ground plane, it's not really going to do anything. So you can probably safely ignore that. But the way to fix that would be, actually, what we could do is we could place a second polygon pore on the bottom layer. So if we select the bottom layer, polygon pore, this is sometimes not recommended for various things, but yeah, it's not super critical if you're not following along some of this stuff. But you can see now we've got a ground plane on both. You could do a power plane on the top layer and a ground plane on the bottom layer if you wanted to. But okay, so now we've just got the minimum solder mask sliver issue, which is annoying, but we're not going to fix because it's a bit fiddly. Cool. That pretty much wraps it up. I think in the Nuclino, did anyone have any questions?
A really weird question.
Yeah.
If an IC has like 2 pins that are like, you always have to connect these together. Why don't they just, why are they even pins? Why don't they just connect them inside and, you know, hide that from the...
I don't know, actually. It's a good question. You'd think they would. I'd imagine during the design, they like thought they might need to add some passives to it, like a capacitor or something, or a resistor in between it. But then it turned out they didn't, or something like that. I'm not exactly sure.
Okay.
It could be, Alex, for like future implementation with the IC. So they've got like plans in the future, they might use those pins for something else. Or it could also be, there might be different functions on the IC. So if you're using the IC a certain way, you might want to short them together. But if you're using it another way, you might route them differently.
Oh, yeah, that all makes sense. Thanks.
Once you've finished your board and you've run your design rules and it's all passed, Christos has made videos on Nuclino under release project and generate outputs on how to export them for manufacture. So I won't go through it here because the video is pretty good, but you can check that out. Yeah, what I might do is I might just show you how you would fix this. So if we go to the components, it's the CCS 811. So we'd right click and edit. So if you went to the component workshop yesterday, you'll see how to actually make these. And we're going to edit the footprint here. So I'm going to click edit on that. And now the issue was the solder mask sliver was the solder mask was like too thin. What I'm going to do is I'm just going to select all the pads, and down here, solder mask expansion. On this IC, it's defaulted to 0.5 millimeters from the pads. we're just going to change this to be 0. And now there is no paste mask expansion. You could probably tune that to be closer to what you want, but closer to exactly the capability of JLC, but it's probably fine. So then we can close that and save this and save it to server. And we'll just say updated solder mask. Now the thing is, so now we've changed our component in the workspace, but we haven't changed it in the PCB, and we haven't even changed it in our schematic yet. So if we go back to the sensor schematic, we can then right click on here and go sheet part actions, update selected from libraries. And you can see there's this one change here, which is the CCS 811. And we just go next, finish. And then it gives us this engineering change order, modify U4, we execute. And now this component with it has a new footprint, but our PCB isn't even updated yet. So we need to go design, import changes. Now, one thing, when you're importing changes from your schematic, it'll add all these rooms back in, which went away when we imported our design rules. Generally, I'd recommend keeping your rooms together while you're sort of laying out components. And then once you've done the layout, then you can remove it. If you've got multiples of the same room, you can apply the same layout from one room to the others, which can be helpful. So if I execute this with the room changes, it's like, oh my God, everything's an error. What's going on? And the reason is it's put the rooms here and it's complaining that all the components aren't in their right rooms. So I'm just going to select all of these and delete them. And now it is complaining about what? Is it the polygon pour? Oh yeah, polygon not poured. So if we re-pour that, and there we go. So it had to re-pour the polygon because the footprint changed. And now you can see we hopefully no longer have that error. Okay, we still do. Cool. So this is at the point where, it's complaining about the pick as well. Okay. So you can see all the layers here. If we go to top solder. Right. So, well, I guess I can do the same thing for the pick as well. So we can grab the part number. The other thing you could do, so I'll show you the JLC. If you Google JLC PCB capabilities, you'll see where we get all these values from. So there's like minimum drill hole size. So like your holes can be minimum 0.2 millimeters and maximum 6.3 millimeters. So it'll give you an error if you exceed that. So if we go to minimum, so solder mask, you can see here there's a 0.2, the spacing between copper pads edge must be 0.2 millimeters or more. So it's actually different to the solder mask sliver. So we can probably update that rule. Oh, here you go. Okay. So it turns out our rules are bad. That's interesting. So these rules are wrong. We can probably get rid of the solder mask sliver rule and just, so it's actually saying that the solder mask should be 0.05 millimeters bigger than the pad to allow for any misregistration, which means when the solder mask layer doesn't align properly with the copper layer underneath. So I will update our design rules for that, but I will do that at another point. But yeah, that's basically the whole process. So you can ogle at your board in 3D. The 3D view is a bit weird. I'm kind of stuck. There we go. Yeah, any final questions? While we've got a couple of minutes, I might just show you what sort of the extreme of this is with some of the boards we've done. So the Jetson carrier board we designed last year. Yikes. Okay. So yeah, the Jetson carrier board here, you can see has 27 schematic sheets. So it's quite extreme, and that's what the top level sheet looks like. So you can see we've done all this modularity and sort of information flow. I won't go into any of the gory details, but this is what the board looks like. It takes a second to load because it's quite a bit. So yeah, sort of the extreme layer of where you go. So you can see we've got similar sort of like these are CAN transceivers here, so you can see all the stuff there. This is like the HDMI circuit. So all it's all exactly the same sort of stuff. It's just this is an extreme version. So when you add it all up, it gets quite complicated. So yeah, this is where you can be in a couple of years, if you can. Cool. Well, I guess we'll wrap it up there if anyone's no more final questions. Alrighty.